Over the past couple of days, you've been working with finding the derivatives to expressions and equations that involve both the natural log as well as logarithms with different bases. So what I'd like for you to do now is to consider this as a video to help us to pre-plan some of the work that we'll tackle in class tomorrow. In fact, we'll have you work as groups, work at these problems, and have that culminate in curve sketching. Okay, so let's consider the first example, and we'll simply do some pre-planning, and we'll tackle the rest tomorrow in our groups. So I need you to find the equation of the tangent line to a y equals log x to the base 2 at the specific point 8, 3. Okay, so let's have a look at some ideas. So let's give a shout out here to maybe one step, and that is to say that it would be useful to find the derivative of y with respect to x. Okay. Now, if you kind of plan this with me, maybe pause the video here and there so it gives you an opportunity to think about what comes next, and you might even go so far as to act out on that. Step number 2, that is to find dy by dx, requires some specific knowledge. So what is that particular knowledge? Do recall that when working with a log or logarithmic expression, when you find the derivative, okay, so the derivative of any log, that is to any particular base, is going to be equal to 1 over x ln b. Okay, so now that we have the derivative within our reach, once we find it, do recall that thirdly, that represents the slope of tangent. So let's deal with slope. So I'm going to need you to evaluate or find dy by dx at x equals 8. That is at the value of the independent variable. And last but not least, I know that you would then act out upon this particular step. And fourth and final, you do need the equation of the line. So recall that we've been using the point slope equation of the line. Y minus y1 equals the slope multiplied by x minus x1. Okay, so we'll carry on with that tomorrow. What we'll do now is we'll consider example number 2, and we'll do a bit of pre-planning with this one. Okay, so with this example, we're going to find the absolute minimum value of the following function. Y equals x multiplied by ln x. So this is a product. Okay. Whoops. We've got some material here on screen that doesn't need to be there. Much better. Okay. So this is a product that we're using. So x multiplied by ln x. So do take note that with some of these functions, log x, ln x, we know that there are restrictions on the domain. So even when we have a combined function like x multiplied by the ln of x, we do have to appreciate that there is a restriction on its domain. So we know that for ln x, x must be greater than 0. We do know that for x, that the domain of that function is all of r. So the domain of the combined function is reliant on the restriction of ln x. So x must be bigger than 0. That's going to play a key role when we are looking at the minimum value, and specifically the absolute minimum value. Okay, we'll come back to that in a little while. So let's do some pre-planning. So let's get a few steps set up here. So number one, if we are after the minimum, okay, then we are clearly in the business of finding dy by dx. And because our combined function includes multiplication, then we are going to be enacting the product rule. Okay, so also recognize that when using the product rule, that the derivative of ln x, according to our rules, is 1 over x. So once we have that in place, you probably remember quite well that the next step in the process is then to search for critical values. Okay, in fact, we are looking for a critical value. What is that value going to be? So recall how we would set dy by dx to 0 and solve, okay, in order to find the critical value. So there's some particular value of x that is going to produce the absolute minimum in this case. Okay, so then once we have that in place, okay, you'd have the critical value, which is the x coordinate for that particular local, well in this case it'll be an absolute extreme, okay, not just a local minimum, but it's supposed to be the absolute in this case. What we would do is we would then go after the y value. Okay, so we need the corresponding y value to the solution that we just came up with. So to the solution of dy by dx equals 0. Okay, we're going to need that. And once that's been put into place, okay, let's grab another cal out here. We'll continue with our steps here. So then our fifth step, we would now have the coordinates for that particular minimum. Okay, we'd want to test that it's a minimum, so we could go second deriv. Okay, so d2y by dx squared, so we can figure that out. Once that's figured out, we can then test, right? We can test the critical value in that function. So in the function d2y by dx squared. Okay. Based on the results, right? Recall that if, let's go off to the side here. So if d2y by dx2 for a particular critical value of x, whatever that number is, was greater than 0, right? That implied that you would have a min. Okay, so positive value when evaluating the second derivative for the critical value gives you a positive. You're going to have a minimum. So that'll be good news if we test it and we come up with that. Aside from that, if we go a little bit further in terms of lining out some steps, let's bring this down into play here. Another step in the process is to confirm the nature of that particular point. So is it the absolute min, or are there other values? So what we do need to do is test, okay, we do need to test values about the proposed minimum. Okay, so we want to test values about the minimum to see if they're going to be greater than the value of our minimum. Okay, so we're really trying, what does that imply? We want to see, okay, um, do the surrounding y values surpass? Are they greater than? Greater than? Are they greater than? So do they surpass the minimum value? Okay, so are they above it? If so, then we have our absolute minimum. Last but not least, and this isn't necessary for this solution, but visually speaking, it might actually offer a bonus in this case. So this will be the 8th step. What you really should do is you should graph, you know, both y and y prime. And the reason why I say that is that some of these functions, if you have a visual representation for it, then it can inform the algebra that you do and vice versa. And also, you're going to end up getting critical values that are different than what you've experienced before. And knowing where they actually occur on a graph in relation to it is critical. Okay, so give that a try. Okay, let's look at our final example where we're going to determine the intervals of concavity for the following functions. So we are looking at where the function f of x is concave up and concave down. So again, let's start by addressing the domain of this function. Recognize that it is to a combination. We have x multiplied by e to the x. We know that x is defined for all values, as well as e to the x is defined for all real values. So I think we can appreciate that the domain is xer. As far as the steps are concerned, let's take a bit of a walk down memory lane, and let's consider firstly, if we're after concavity, we're going to need the first derivative, dy by dx. So given that we're presented with function notation, we're looking at f prime at x. Secondly, if we're after concavity, then we do need the second derivative. So f double prime at x. Now, knowing that we're again on the hunt for concavity, we do need inflection points. So the values that are critical as being inflection points. Okay, so inflection points. Remember that this is where you have a solution to the equation f double prime at x is equal to 0. Once you have those solutions, you got into the habit of testing particular intervals and drawing a conclusion based on the results of your interval table. So, interval table is what's next. So let's just go down here in the space below, and we will outline or review the structure of that particular table. So recall that with your table, you'd end up with particular intervals. So you'd have, generally speaking, a number greater than x. So you'd be looking to the left of a particular critical value. That would be followed by, depending on how many you have, you'd oftentimes have one in between and one that went beyond. So there could be anywhere from one to many critical values, but that depends on the solution to this equation up here. Down the left-hand side, we often had a test value in our table. Okay, so we would choose a value within the interval, substitute that into the second derivative equation, and look at the result. Specifically, as opposed to into the equation directly, we would write down the factors of that particular equation and determine their sign. So depending on how many factors you have. Following that, what we would do is we would look at the sign of the factor, the sign of the product of the factors, and if it was positive, right, we would say that in terms of the concavity, that would be concave up. So the final row in our table was with respect to concavity. If it was negative, concave down. So I'm going to have you put all of these skills together. So it is in review, but it is also being applied to a different set of functions. And your work tomorrow will culminate with some graph analysis. So I'm going to have you analyze the curve y equals x multiplied by e to the x squared under these particular areas. So each of these criteria I'll have you address in order to produce a sketch.